then. So last time we started talking about software development and we covered multiple software development lifecycle methodologies. And it really wasn't the most exciting topic. I know we have to learn this for the exam, but it doesn't really help us understand how to code an application in a secure manner. So that's precisely what we're going to be talking about today. Also, apologies for my voice. My sinuses have decided not to be YouTube friendly today, but hopefully the content is still going to be clear. So thank you. So let's talk about coding securely, or how do we write those applications so that they are secure? And I would like to start with one idea. And this idea is actually so important because, how should I put this? If we manage to fix this one single thing in every single application that we develop, then 90% of all these cybersecurity analysts out there would suddenly be without a job. And that single idea is called input validation. And I cannot stress this enough. This is the number one method, the number one best practice to get rid of a lot of vulnerabilities in your code, because a lot of problems appear when you ask for input from your users. And if you look over the vulnerability databases out there, just randomly search for one vulnerability, and you're going to find in most cases that it's going to be about a crafted request, a malformed request, a specific type of file that is sent to that application, a specific crafted packet or malformed, I don't know, protocol anomaly that is sent to that application and that eventually exploits a vulnerability. So it's all about accepting input and not validating it properly when it comes from your users. And this is where most vulnerabilities originate from. And if you're thinking, all right, I don't have that much input in my application, or I don't have any input in my application. Well, you do. Even if you're just serving static pages, even though probably you won't call that an application, but even for a static page, you're going to accept an HTTP request that's going to be processed, and then it's going to return a specific static page. Well, that HTTP request is a kind of input. If you allow users to submit comments on a shopping website, for example, that's going to be input. If you allow users to configure their profiles and upload their profile pictures or their resumes, for example, on a website, that's going to be input. That's going to be a vulnerability that can be potentially exploited. Now, there are a lot of places online where you can find documentation about what you should be looking for when you plan to do input validation. And this is actually because it's such a wide topic that it's basically impossible to cover in one single place, especially because it applies in a different manner to web application, in another manner to mobile applications, in another way to, I don't know, server-side applications, for example. It depends so much on the type of application and the type of input that you're expecting. But it all boils down to deciding what type of input you expect to receive from your users, and then making absolutely sure that the input that you're receiving is thoroughly checked and validated, just to make sure that you're receiving what you expect to receive, and not something else, not something bigger, not something executable when it should be a picture, or that it's not an Office document with a macro, that it's not a number instead of a string. OWASP points for us a couple of things to keep in mind. For example, we first have syntactic validation, which ensures that we're actually looking at something that is supposed to be looking as a date, as an age, or as an address, or a social security number, or a passport number, or something like that. Semantic validation means that we need to enforce the correctness of their values in their specific context. That is, abnormal dates or abnormal quantities for a product, or negative quantities for a product. They're discussing here multiple ways of validating based on allow lists or block lists. Most of the cases you're going to want to rely on allow lists because it's much easier to specify what exactly is valid for your context rather than trying to define everything that isn't valid. Regular expressions, for example, are very used for situations where you know exactly how the input should look like, or at least how it should be structured. They talk about sanitizing HTML, verifying every file that gets uploaded by your users. And it's so much to cover simply because most applications have multiple points of entries. They have multiple interfaces with the outside world that accept input from your users. And it's very important to decide what are all the potential inputs to your application. Yeah, you can have users submitting HTTP requests, uploading files, submitting forms, but you can also have a third-party connection with a storage cloud service, for example, that you're thinking that you're only using that interface to communicate with the cloud service, but can you be 100% sure that an attacker is not going to be able to craft a request and send it through that same interface as well? And speaking about crafting requests, never, absolutely never, input validate on the client side. That is, don't use the client application or the client's browser to make the necessary checks in order to make sure that the data that you're receiving from the user is valid and doesn't contain any malicious code. Kind of obvious why we do this, right? Because every check that we expect to do on the client side can be easily circumvented by an attacker. Let's say, for example, that we have an online store and we're running a promotion. We only want to let users order one single item of a specific category. Well, if you make this check on the browser side, well, the normal user is going to see that when they try to add the second item, they're going to get an error and the number comes back to 1. But an attacker can also craft the same request that your browser is supposed to be sending and can change that request to say 100 items, 1,000,000 items. If you don't make any checks on the server side when the request comes in to your e-commerce application, you're going to end up with an order of 1,000,000 items, which is most likely something you don't want. So basically, we're never validating on the client side because a potential attacker has the option of choosing their own client to build those requests and circumvent any checks that we might have in place. So for web forms, at least, you're gonna have to make sure that you're checking the data type that you're receiving, like a person's name only includes letters, a date is between a minimum and a maximum. So for every piece of information that you receive from the client, you should check on the server side if it falls within a predefined numerical range, for example, for an age, for a quantity. Make sure you don't get huge numbers, make sure you don't get negative values. When users upload files, make sure that you're not receiving, again, huge files, and also check the files to make sure that they're actually the valid types that you're expecting, right? That a profile picture is a JPEG or a PNG file, and I don't know, a resume is a PDF file and not something else. And as mentioned before, it's much easier to have a whitelist approach to this types of checking because it's much easier to decide, well, this is exactly what I expect to receive in this field right here, rather than thinking about all the potential junk that your users might try to submit or to upload to your web application. As mentioned, input validation can be as simple as validating the HTTP requests that your users are sending. So for example, in this simple HTTP request here, let's assume that I have a website that stores some user profiles, and if I'm logged in as Andre, as my name here, then I should be able to access, using a specific query like this, my own profile picture. Now, an improperly coded application might allow me to actually try to generate some other valid URLs like this. So for example, if I change the file name to something that's Robert's profile picture here, and I shouldn't be able to access that information, well, the application should validate its request and deny me access to some other user's profile information. This would be most likely a way of circumventing authentication and a proof of broken authentication in our app. Now, going one step further, instead of just specifying the file that I want to access, I could try navigating the file system on the web server, and I could try accessing some files I should have no business accessing. This one is called directory traversal. So it's the ability of the user to actually navigate through the file system of the web server in order to access different types of information. I can think about doing even more. I mean, if directory traversal works, then I should be able to reach any location on the web server as well, as long as the web server application that's hosting the web application actually has enough privileges to access those locations and to open specific files. So for example, I can actually read something like Etsy password, which doesn't really store passwords, as you probably know, but it does give me a listing of all the users and their privileges on that specific web server, which is a great first step in reconnaissance and preparing to break into that web server. And by now you're probably thinking, well, this directory traversal vulnerability is easily mitigated simply by not accepting dots and slashes in the path that specifies the profile picture, right? Well, what if I do this? This one is called HTML encoding. As you can probably guess, %2e is going to be interpreted as a dot, and %2f is going to be interpreted as a slash. Now, your fancy regular expression, which just looks for dots and slashes, has suddenly been defeated, right? This string right here is going to be interpreted correctly by the web browser, but it doesn't match your input validation method. So careful about this one as well. Think about all the possible ways in which the characters or the input that comes from your users can be encoded. Think about the fact that users might submit their content in an encrypted format, or using base64 encoding, or any other type of encoding out there that it's not going to be detected by your basic input validation tools, but might be properly processed and perhaps even executed by the web application. Well, if we have to be careful about input, we should also be careful about output. And applications will generate output. They will present back information to the user. Well, if that information includes some piece of code, for example, a JavaScript code that gets executed by the user's browser, and that code is malicious, well, we have a problem. We have a vulnerability. Well, malicious output, of course, doesn't just magically appear. Most likely, you're going to have malicious output if you failed to properly sanitize or validate the input. So at some point, some malicious user, some attacker was able to inject that code and manage to bypass your input validation procedures, so that when another user comes in and accesses your website, they're going to be presented with that malicious code, and of course the code is going to infect their browsers or their systems. And this is one of the methods for mitigating cross-site scripting. Now we're going to talk about cross-site scripting in a future video, but just to keep things short, imagine you have a, let's say, a commercial website, an online store, and you let your users submit comments on your product, right? Now the comments should normally be just a couple of English sentences, but let's say that an attacker includes not only a couple of English sentences, but also a piece of malicious JavaScript code in their comment. Now that JavaScript code, if it's not properly sanitized, is going to be stored in the database along with the main comment. So when another user comes in and tries to access the list of comments for that specific product, well, the database is going to return the entire list of comments, and one specific comment is going to have a couple of English sentences and also a piece of malicious JavaScript code, which the user is not going to see, because the JavaScript code is supposed to be seen only by the browser and executed by the browser. And when the browser gets that code along with the comment, sees, oh, this is some dynamic piece of code that I need to execute on this web page, goes ahead and executes that code without providing any feedback to the user. And if that malicious code, for example, downloads some additional malware, or steals some personal data, steals some cookies and login credentials or anything else, this can happen without the user knowing about it at all. So this is the definition actually of a stored cross-site scripting attack. And one way we can avoid this is to make sure that when we are displaying that information back to the user, when we're rendering the page, we're not processing any dynamic code that we find within those comment sections. So if we find some JavaScript code in there, we're going to escape those special characters so that the browser is not going to recognize those script tags in there, and it's not going to try to execute them. They're simply going to display the code just like a regular comment. So one way of explaining this is to make sure that whenever you're outputting some information back to the user, you remove, or you scan and parse that code to remove anything that can be potentially executed by the client application. Now, communication security is kind of obvious, right? If the application transfers some sort of data or accepts some sort of data from the users, well, of course, we're gonna want to secure that data when it is moving, or another way of saying this is secure data in transit. How do we do this? Well, in most cases, especially for web applications, but also for mobile applications nowadays as well, we're going to use TLS, which is the evolution of SSL. Sometimes you're going to see it referenced as SSL, but it's not SSL anymore, hasn't been for a couple of years, so it's basically now TLS, which was the old SSL. Now TLS relies on public key cryptography, which allows us not only to ensure that the data can be encrypted, so it cannot be sniffed or intercepted while in transit, but also allows us to authenticate the integrity of the data as well as the identity of the entities that are communicating. So I can authenticate myself to the web server, and the web server can authenticate itself to me so that I'm sure I'm actually talking to the right entity and not to an attacker who pretends to be that web server. So TLS brings us a lot of benefits in one package. And one way TLS does this, and actually the one way that public key cryptography can be easily implemented nowadays, is by using certificates, digital certificates. Now, if you're using TLS with your websites, then your website is actually going to be accessed through the HTTPS protocol. So you're going to see an HTTPS:// before your website address. Ideally, the certificate is going to be valid, it's going to be recognized by a public CA, and also make sure on the coding side that your application never falls back to pure HTTP. So make sure that a user cannot choose to start using HTTP instead of HTTPS. Not even for small pieces of information like cookies or JavaScript or CSS files. There's actually a specific type of attack technique called protocol downgrade, which, especially for security protocols like HTTPS, relies on the fact that some implementations or some applications allow you to choose the security protocol, or even to choose a protocol that doesn't implement security at all. So make sure you don't allow your users to fall back to an unsecure version of communication. And even if you don't allow users to fall back to HTTP, make sure you also specify exactly which encryption algorithms and which key lengths are going to be accepted when communicating over HTTPS, because protocol downgrade can also rely on the fact that the server allows clients to negotiate those security parameters, and an attacker might attempt to first negotiate the lowest possible security protocol acceptable by the web server, because that lowest one is probably going to be the easiest one to crack, or at least to run some cryptanalysis on it. Session management is another point of interest for developing especially web applications. What exactly is a session? Well, the session is actually a random number, random ID that is assigned to you and also stored on the server the first time you communicate with that server, and also probably the first time you authenticate with that server. The purpose of the session is that whenever you're sending some subsequent requests to the same web server, you're going to include that single session ID in all your future requests. Well, when the web server sees that session ID in your requests, then the web server is going to know that all these requests come from the same person. So it's able to store state information about yourself, is going to store your, let's say, navigation history, maybe your shopping cart, and everything else that pertains to your specific identity when navigating that website. So on the coding side, the problem actually is, how do you generate those session IDs? Ideally, they should be generated on a trusted system separate from your web application, and you should be using some good algorithms to generate those session IDs so that they cannot be guessed by some other user, or God forbid, that they're not sequential. Because the session ID, you have to treat it actually as a password. Think of it as a password, because if somebody else knows your session ID, then any requests that that person or that attacker is going to send using your session ID are going to be processed by the web server as if they're coming from you. So basically, stealing a session ID is kind of like impersonating someone when accessing a web application. I probably don't have to add that session IDs should not be visible, so they shouldn't be included in the URL at any point. They shouldn't be visible in the profile page, right? And I stress this again, don't make them guessable, don't make them easy to guess. A lot of people, when they're just starting to develop web applications, are going to think about, well, what's an easy way to generate a unique value every single time I generate a new session ID? Well, I'm going to use the timestamp, the current second or the current millisecond. Well, that's a value that can be easily guessed by an attacker, right? If that value is guessed by an attacker, then the attacker can send requests on your behalf and basically impersonate you. Of course, sessions should expire. You probably see this on all websites. If you don't send any requests for a specific length of time, you're going to be kicked out and you have to re-authenticate. Sessions should expire because the longer a session is valid, the higher the risk of that session ID being compromised and used sometime in the future by a malicious attacker. Also, a good practice would be to try to use different session IDs for different level of privileges. So once you might be authenticated as a normal user, you get a session ID, but the moment you escalate that privilege, if you authenticate yourself as an admin user or as a root user for that specific web application, a new session ID should be generated. because you're basically a different person now with a different set of permissions, different set of privileges. And especially if you're using privileged accounts, think about periodically expiring those sessions, even if you are receiving active input from the user, because especially for very long sessions, if you need to have a long session in there, if you generate a session for 8 hours, can you be 100% sure that during those 8 hours that admin hasn't left the desk and somebody else hasn't started using that machine in the meantime? So periodically try to expire sessions and ask the user to re-authenticate just to revalidate that they're still who they claim to be. Don't forget to implement a logout function from your application, even if 90% of users don't use it, but make sure it is properly implemented, as in it completely invalidates all the session information, so it deletes everything related to active sessions. That's basically what the logout function does every single time. It deletes the session information from the server. Think about if you want to allow users to have multiple simultaneous sessions to your web application at the same time. How do you manage sessions in that situation? Or would you rather invalidate the old session every single time a new user logs in on a new machine? Well, think about that depending on your security requirements. And when it comes to securing session information, most web applications are going to rely on HTTP cookies for this type of information. And we have a couple of flags or attributes, two of them being secure and HTTP only, which help us with protecting the information in those cookies. Now what they do, and this is actually important for the exam as well, most likely you're going to be asked about this. Well, the secure attribute is sent to the server only with an encrypted request over the HTTPS protocol, which means that the cookie is going to travel over an encrypted channel, which is ideal, right? Make sure you don't send any other piece of information outside HTTPS. If you use HTTPS, try to send all the information through that encrypted tunnel. Now, on the other hand, the HTTP only attribute makes that cookie inaccessible to any JavaScript code, specifically the document.cookie property, which means that the only way of accessing that cookie is to use it in an HTTP request that goes to the proper server. So a malicious JavaScript code that might be injected in the web page cannot read that cookie information and cannot transmit it to a potential attacker that could impersonate you. Now, when it comes to authentication, and authentication is basically the process of proving who you are, obviously you should use authentication for any access to any resource that needs to be protected. So if a user tries to access some piece of information that is located in some place where only authenticated users should have access, well, then make sure that the user is properly authenticated before granting access to that specific resource or file or database entry. Don't forget about MFA, which is multi-factor authentication or two-factor authentication, depending on how many factors you have. Make sure that you implement it in your applications, because this is a great way to properly secure your login credentials. With MFA, if your username and your password get compromised, an attacker still cannot gain access to the system, because they're also going to need the second factor. The second factor can be a biometric authentication, can be something you have, like a token generator, which can also be just an application on your smartphone. The idea is that the attacker has to have two pieces of information, something that you have, something that you know, or something that you are, in order to gain access. Compromising just one single of these factors is not going to be enough to provide access to the application. From a security perspective, try to have the authentication system and the place where you store the users, their credentials, and everything else related to authentication on a separate system, so that is not going to be exposed in case a vulnerability in your web application gets exploited. Fail gracefully sounds cute, right? Actually means that in case the user doesn't get authenticated or the user receives an error while trying to authenticate, make sure that you're not providing too much information to that user. So for example, if the user is correct, but the password is wrong, don't tell this to the user. Don't let him or her know that they managed to input a correct username and they just mistyped a password, because this is going to help someone who's trying to break into your system and say, oh, look at that. So I managed to find a valid username. Let's just focus on the password now. And also don't forget to detect failed login attempts. Too many failed logins from the same user, from the same IP address, using the same session ID even, should have some sort of consequence, which can be as simple as implementing a backup algorithm. Like if you try to input your PIN in your smartphone multiple times in a row, make multiple mistakes, then you're gonna see that the phone actually forces you to wait a couple of seconds first, then a couple of minutes later before you can try again. This back off behavior is basically there to avoid brute force attempts where a huge number of passwords or combinations is attempted in a short time frame. Don't forget about external systems. Your application might use additional databases, external databases, or email services, or cloud storage, or even other cloud resources. Access to those systems also has to be authenticated. So don't accept unauthenticated requests on any external interface that your application might have. What about storing credentials? Well, you have to allow users to create a profile and then set a password, so you'll have to store that password somehow. Never, ever store the password in clear text, and don't even store it in an encrypted format. Actually, don't even store it in a way that can be reversed. So whenever you store the password information, store it as a hash, a one-way hash. You'll never be able to guess the password from the hash, just in case an attacker manages to obtain access to your profile database that stores those hashes. They're still not going to be able to retrieve their passwords. So always use something like a securing hash algorithm, SHA-256, or any strong hashing algorithm that doesn't allow a potential attacker to deduce the original password from the hash. Actually, don't even send the passwords in clear text, right? Send them over encrypted connections, or even better, just send the hashes to compare the hashes and validate the user identity. But don't forget, always authenticate over encrypted connections. If you want to allow users to reset their own passwords and you want to use security questions, make sure that the information that you require to unlock the password reset page doesn't rely on some publicly available information on the internet. So don't ask them for the name of their pets or the name of their wives or anything like that, which can be easily extracted from social media. If you want to ask your users to update their passwords from time to time, make sure you implement also some password policies in there, especially password complexity, and also try to implement password history. And remember password history as well for the exam, because it's a very strong topic in CompTIA exams every single time. Password history basically says that you're not allowed to reuse any of your previous passwords that you've had before on the same application, on the same website, on the same system. Again, to implement this, you don't actually have to store those previous passwords, just their hashes. It's very useful, if possible, to report to the user when they first log in to your application, when was the last detected login on their user account. This might indicate to the user that somebody has stolen their account or compromised their credentials. Also, you can implement something like how many locations are currently logged in to the same user account. This can be easily done by counting how many session IDs have been generated for that specific user on the server side. If you can, try to also tell your users when was the last time they were detected as being logged in. It's not the best method, but it's going to help provide some confidence that nobody else has been using that account in the meantime. And I'm positive that I don't have to insist on this, but I'm just going to mention here. Don't rely on default credentials and remove or replace those default user accounts that come pre-configured from the factory, from the manufacturer, from the vendor. Another idea here is that whenever a user tries to execute a privileged operation, try to re-authenticate that user every single time a privileged operation is requested. For example, think about websites that ask you to provide your current password before allowing you to change it, to change your password. Right? That's also a way to re-authenticate the user, just to make sure that right now, at that very moment, the right user is performing the operation and not some attacker. And like always, whenever you're reusing software or libraries or source code that you can find online, or you can import that into your project, make sure that the third-party software that you decide to use matches the requirements of your authentication system. So it's not going to act as a backdoor or a way to circumvent or to avoid your authentication system that you have in place. And now about authorization and access control. Now, authorization usually comes after authentication, and the main difference is that while authentication's purpose is for you to prove who you are, while authorization, on the other hand, is deciding what privileges you have after you've proven your identity. So first I prove that I am Andrew, and then, as part of the authorization process, I receive a set of privileges that allow me read, write, execute operations on different objects or network entities and so on. So every single time you have a user that's about to perform a specific type of operation, always check in your code that the operation can be and should be performed by that specific user, that the user is authorized to perform that specific action. And this also applies to machine-to-machine communication. You might have two different applications that communicate to each other using an API. Well, that API is going to support some specific operations. You might not want to expose all the operations, like a root level access to your application, to another third-party app. So make sure you first authenticate, of course, any API access, but you also authorize any request that comes in and have your code check it whether it should be allowed or not. Just like with authentication, the authorization system and all the permissions should be stored someplace else, not on the same place as your main application. Just to be safe in case a user manages to exploit your application, so that they won't have the chance to access the privileges table, for example, and then escalate their own privileges and create users and so on. So keep these systems as separate as possible. And again, just like with authentication, fail securely with authorization as well. So if a user tries to perform an operation and they're not allowed, simply inform them that they are not allowed. That's it. Don't give them any other information regarding their current privileges or what privileges would be required to execute that operation, and so on. Try to keep it to a minimum. And this also applies to machine communication, right? You're going to have error messages generated by APIs as well, so make sure you don't expose too much of your internal infrastructure and your internal authorization and authentication system to the outside world. Nobody needs to know how you manage your users, what kind of permissions you have defined in your system, right? Keep it in-house. And another situation where you have to plan for failure, right, in authorization is what happens if the authorization system doesn't answer, doesn't respond, so it's unavailable. What do you do then? Well, most likely you're not going to just allow everyone to do whatever they want. You're probably going to fall back to a restricted set of users with some locally defined permissions on that machine. So be careful about this. Make sure that your users don't suddenly become privileged whenever the authentication system fails. In web applications, authorization also refers to any attempt of a user to access a specific web resource, like a file, an image, and a database entry, anything that can be accessed through an HTTP request. Make sure that you're not allowing users to directly access protected resources. So a user might just know where is a specific protected resource located. Like, let's say they might know where exactly on the payroll server is the salary table located, the salary Excel file located. When somebody tries to access that location, well, that request has to be authorized. Who are you? Do you have permission to access that folder? Do you have read permission up to that specific file? And is there an access list in there that allows you or denies access for yourself? Now, hiding resources and just assuming that users are not going to discover them unless they're authenticated, that's a way of implementing security by obscurity, and we don't want to do that. That is not security by any means. The number and frequency of the operations has also to be taken into account, because we're not only facing exploitation attacks, but we're also facing denial of service attacks. Right? So you might have a filter in there that checks every operation, and if you're not authorized, then you're going to just receive an error. All right, that works just fine, but what if 1 million requests come in every single second? Well, you're going to try to generate 1 million errors, perform 1 million checks, but that's most likely going to crash your authentication system. So make sure that as part of the authorization system and access control, you're also limiting the rate at which you are accepting for validation requests that are coming in from your users. Now, of course, a very basic one is if you don't need an account anymore, if nobody uses it anymore, even if it's a machine account, it might be a service account that was previously used by some third-party application, retire that account. Doesn't necessarily mean delete it completely, but most operating systems allow you to disable a specific account so that in the future, if somebody realizes that, I don't know, there were some encrypted files that were protected by that specific account, well, you can simply re-enable that old account and decrypt that content. But still, don't forget to retire unused accounts. And of course, something that's most likely the first thing we should have mentioned on this slide is the principle of least privilege. Don't give an entity, a user, a machine, an application, a service, anything, don't give them more permissions than they actually require to do their job. Because all you're doing is just exposing yourself to more and more risk. Now, as part of the low-level coding discussion, of course, there's going to be a lot to discuss here. And since this is not a programming training, I'm just going to mention two of these here. Try avoiding direct system calls. So don't use the system calls of the operating system. Try using APIs, because APIs are going to filter a lot of the, let's say, unwanted calls, or a lot of the illegal use of those system calls. They're going to try to normalize and sanitize that input. So it's going to be another layer of input validation for your own code. Another one is, of course, try to avoid as much as possible race conditions. Now, race condition is also a programming bug or programming mistake, but can also be exploited by an attack. Race condition basically means that two processes, two entities attempt to access the same resource at the same time, and at least one of them also attempts to change that resource. Now, the problem and why it's called a race condition is that it's almost next to impossible, or it's very hard to predict what the end outcome is going to be when those operations happen at the same time. So it's basically a sort of timing bug in your code. Now, in order to avoid this, locking mechanism has to be in place, in which the moment you try to access a resource, you also put a lock on that resource, and only a single process, single user, single application, single anything, an entity can access, read, or change that resource. Now, after the operation has finished, of course, the lock is released and the resource can be used by somebody else. And although this is not part of the software development process, we still have to think about where is our code going to run, on which server, platform, operating system, cloud environment, local environments, user's phone, and so on. And from a security perspective, well, we've talked about this before, but we're going to have to focus on, patching, keeping that platform updated, the operating system up to date, all the things that we know that we're supposed to do in order to keep that attack surface minimal. And keep in mind that if you're running a web application on a web server, on an operating system, then you actually have three platforms, three types of attack surfaces that you have to defend. One is your application. That's going to be your application code, where you have to protect yourself against, buffer overflows, injections, and so on. Secondly, you have the web server itself, which is a standalone application, which is probably not under your control, but you still have to keep it up to date and monitor it for vulnerabilities. And third, you have the entire operating system that hosts everything in there, which also has to be updated with the latest security patches and a proper security-oriented configuration, so that a potential attacker cannot break your code, your web server, or the operating system that's hosting it all. Also, don't forget that a web server is just another type of application that's running on an operating system. If that web server is running your web application, then the web application is going to run with the same privileges on that system as the web server. So in case somebody manages to break the code of your application, perform some code injection, well, that code is going to be executed with whatever permissions the web server has on that machine. I've seen several situations where people are just lazy enough so that, to avoid any conflicts or errors, they simply installed web servers with root privileges. So the web server actually runs as root, which means that whoever manages to exploit any web application hosted by that web server can potentially get root access on that same machine. And that's extremely dangerous. So make sure that the application doesn't run with any system level privileges. So in case somebody exploits that application, they're not going to be able to do anything outside that application's environment. Another one here, pretty much common sense. Don't store test, development, UAT versions of the same application on the same system. Right? Because those are most likely going to have, test accounts, test data. They're probably going to bypass some authentication procedures. And just in case somebody discovers those on your system, they're most likely going to be much easier to exploit than the production application. Use the robots.txt file for search engines, which is going to prevent the disclosure of your website structure to any search engines that might be crawling or spidering your application. So also make sure that all sensitive information is disallowed in this file. So don't allow Google to index any sensitive areas in your application. Also on the chapter of input validation, but this time from a system or infrastructure perspective, you should also restrict the allowed HTTP methods that can be sent towards your applications. You're not going to accept just any kind of request out there. You're just going to accept those requests that have meaning and are useful for your application. Also, don't accept anything below TLS 1.0. And also on the server side, the responses coming in from the web server back to the user are usually going to include some information in the HTTP header. Make sure you inspect that information so it doesn't disclose something that you would not want to be disclosed to your users. For example, make sure that you are not displaying the actual type of web server or the version or the patch level of the web server that you're using to host that application, because that's a gold mine for an attacker. They're going to know exactly which exploit to use according to the version that you have running in there. Well, in most applications, you're going to have at least a small database. So again, since we're talking about data, think about input validation, so validate the input before you're storing it in the database, and also output encoding. So how are you displaying in a safe manner whatever data was stored in the database? And to defend ourselves against injection of foreign code, which in the database world is probably going to be something like an SQL injection or SQL injection, well, the best thing we can do is to properly prepare our queries or database queries. And we're going to find these terms in a lot of places. Some people call them parameterized queries, others call them prepared statements, some languages call them precompiled statements. And again, these are all methods of defending against SQL injection. Now, we're going to talk about SQL injection in a future episode, but for now, just to keep things short, the idea behind these types of queries or statements is that instead of just concatenating what the user sends to the SQL query, the SQL string, we take the user content and we don't interpret it in any way. We simply treat it as text. That way we can avoid the situations where user input gets to be treated as SQL or partial SQL statements. So what these statements do is that they include placeholders for these parameters, the parameters that come from the user side. So when the query is executed, the application binds the actual values provided by the users to these parameters. So all those special characters that you're going to find in SQL injection attempts are no longer interpreted by the SQL server, but are taken literally as pure text. I'm sure I don't need to mention this here again, but apply this privilege to databases as well, because you're storing data and people should not have access to all data in the world, right? One user should have a set of privileges, and another user should have a different set of privileges, which dictate which type of data they are allowed to access and also which type of data they're allowed to modify. Don't hard code database credentials in your application code, because if your application gets exploited and somebody gets to read the source code file, you've just given them access to the database as well. Now, there are solutions out there that help you securely store such authentication credentials, like HashiCorp Vault, for example, and many other solutions out there. Long story short, just don't hard code usernames and passwords into your application. Just like with third-party code, don't forget about default databases, default tables, demo data that might come from the default installation of the database server. Don't keep them there, because those tables, those databases might allow some users to perform some unintended operations. And the worst part is that you might even completely forget about those when you're building your authentication mechanisms, your authorization policies. Disable any additional database system functionality that might be available by default. What I mean by this is that some database engines even allow you to execute system calls or to run executables on the same system as the database. If somebody manages to perform an SQL injection and to run their own queries, well, those queries might include a command to be executed on the database server, which leads to privilege escalation, which of course leads to the server being fully compromised under the attacker's control. And generally, when you have multiple applications that are using the same database system, make sure that each application uses their own database. Firstly, because it's much easier to create security policies, which application has which permissions on which database. And secondly, because you isolate, let's say, vulnerability domains. If an attacker manages to crack an application and gain access to its database, at least it's not going to have access to the rest of the data of the other applications that are running on the same system. And when we're talking about pure data, information, files, of course, the first thing that comes into mind is least privilege. Do I need to say more about this? No. And the main idea here is that when you want to protect data, the first thing that should come into mind is encryption. Encrypt it so that nobody can read that information. And a very big benefit of encryption is not only the fact that it hides information, but it also protects that information from outside tampering. So somebody else cannot just come in and change that information without you knowing about this or without corrupting it. Because in order to properly change a file that has been encrypted, you first have to decrypt it. You have to have the decryption key in order to perform those changes, and then you have to use probably the same key or another key to encrypt it back again. That's also one of the benefits of encryption, right? Making your data tamper-proof. Now, the discussion about encryption can be a very long one, but some things to keep in mind. For example, choose strong encryption ciphers. As technology evolves, older ciphers get easier and easier to crack. So always make sure that you're using something that's adequate for the present time and perhaps for the next 5 years. Make sure you have a process in place for key management. How do you store those encryption keys? Who has access to them, and how, when, which type of authentication system you're going to use for somebody who needs access to such an encryption key. And for very, very critical systems, careful with random number generators, because a large part of cryptography actually relies on generating very large random numbers, and computers are inherently bad at generating random numbers simply because everything is deterministic. But this is another talk for another time. Careful with caches and temporary files that your application might be writing to disk from time to time, especially if it's writing that information on the client's disk. So for example, it's using the browser's cache or the mobile phone's cache to write some temporary files that are currently in use. Those files can very easily contain sensitive information, or at least some information that can be used by a potential attacker to impersonate you, to break into your account, or to perform some operations on your behalf. So make sure that the application thoroughly cleans after itself and you're not storing sensitive data on the user device. Now, if your application is not open source, make sure you protect the source code. Also, if you're a web application, make sure that users cannot somehow circumvent the web server and access the source code files directly. Normal users should not be able to see the PHP files, the ASP files that the application is currently executing, that the web server is running. They're only supposed to see the result generated by those files. As a general rule, of course, don't store sensitive data in clear text. Actually, whenever you're moving data, whenever you're storing data, always protect it. And coming back to that input validation idea at the beginning of this video, always validate whatever input, whatever data you receive from the users. And don't allow anything that has a potential of being executable code to come in and be processed by your application. So validate any user files that come in, anything that user uploads. Make sure that the file type is the one that you expect. And don't just look at the extension, because anybody can change an extension. Look at the actual binary representation of the file. Look for a specific header that tells you that that file is either an image, a document, or an executable file hidden within an image. Also, against code injection attacks, don't store user data in the same place as the application data. Actually, don't store anything that you receive from your users in the same place as your application code, because you might receive something very bad from the users. And you don't want to store malware right next to your application data. Also, on the data protection part, think about the data that the application has to access. So for example, the application might need to load some external libraries, some external files, and use them in its day-to-day operations. Ideally, these references should be hard-coded and thoroughly checked. So don't just design an application that blindly loads any type of DLL file that it finds in a specific folder, but design it so that it's looking for a specific type of file, and ideally it's also going to check the hash value of that file to make sure that the file that's getting loaded is actually the one expected by the application. Now, this does require a lot of additional work on the programming side, but the advantage is that this is how you avoid injection of foreign files into your application code. And of course, just in case some user, some attack succeeds and an attacker manages to execute some code in your own application, then at least make sure that the application itself doesn't have write permissions onto its own files. So the application cannot change itself, cannot overwrite itself. So it should only have read-only